has a frequency of 440 hertz. What does that mean?
Yeah, I have a few things I could say about this. So let's see where to start. So I guess I'll start with what sound is, right? So a musical note is a form of sound, specific form of sound, and sound in general, as we experience it, is pressure waves moving through the air. So, for example, right now I'm talking, and my vocal cords are helping to create those pressure waves, and I'm literally sending waves through the air in front of me that reach my microphone, and then eventually your ear. But that's what sound is. It's these pressure waves traveling through the air, and if we understand sort of the form that the waves take, we can think a little bit about what frequency really is. So if we could jump to my screen really fast. This is a basic diagram of a wave. It shows sort of the idea of oscillation. Waves go back and forth. In the case of pressure waves, they go back and forth between being high pressure and low pressure. So we can imagine this diagram as it goes up, we reach the point of highest pressure, and as it comes down, we reach the point of lowest pressure. So in any case, we represent waves with this pattern. We represent waves this way, whether we're talking about sound waves or we could be talking about ocean waves, we could be talking about light waves. But the important things to see here are that there's a couple parts of the wave. So we define the wavelength as the distance from a point on a wave to the point on that same point on the next wave in the sequence. So for example, the top of this wave crest to the top of this next wave crest. That's the distance of the wavelength. We could also say from the beginning of this wave to the end of the wave, and then you can see there's another entire wave cycle right here. So there's two full wave cycles shown in this diagram. So the question it asked, what does 440 hertz mean? Well, so 440 hertz is a musical note. It's actually a famous musical note. It's the note A. I mean, it's often used for tuning. People will say, oh, tune to 440A. But what 440 hertz means is that there are 440 cycles of the wave, of that particular note, wave per second. So a single hertz would be one cycle or one wave per second. In my diagram that you can see here, we've got two waves shown in the diagram, and you can see above that it says the time for this would have been 1 second. So since there's two waves that occupy the space of 1 second, this wave would have a frequency of 2 hertz. Again, going back to our example, 440 hertz is going to be 440 waves per second. So if we look at this diagram, this also just shows like several different frequencies. These are actually all A notes. So we have a low A, 110 hertz, and then a slightly higher A, 220 hertz, and then 440, and then 880 hertz. So as we increase in hertz, where we're increasing in frequency, what you should notice about the different waves is they get bunched together more. That wavelength that I talked about a minute ago gets reduced. So the higher the frequency of a wave, the shorter the wavelength of that wave. And the idea here goes that all sounds, whether it's a low A note or a high A note, whether it's my voice or Becca's voice, they all travel, all these sounds travel at the same speed, meaning that they move forward in space at the same rate. But in the case of a wave like this 880 hertz wave, you get more wave cycles per second of time moving forward than you would with this 110 hertz wave. So that's sort of the distinction there. Briefly, I just wanted to make a plug for this interactive simulation. There's a really great website maintained by the University of Colorado called PhET Simulations. And there's tons of interactive online simulations to learn about different things through science. I use this with my physics students when we studied waves recently.
Who made it?
Who made this?
We made it.
You made it.
We did. With the fish.
With the fish.
Yeah, we did that.
Yeah. So yes, there was another thing we did, was where we made waves on a string using Swedish fish and skewers and duct tape. And if you're interested in checking that out, I don't know what the date of that show would have been, but I'll ask Nancy, our producer, to maybe put it in the comments on one of the videos we post. But in any case, you can go back and check us out doing that in a science experiment. But this simulation, if you can't build a full-on fish wave machine, this would be a good way to do it. So what am I trying to do here? Oh, loop, no end. So this is kind of a neat interactive simulator because you can just sort of see what waves look like. These are waves being produced on a string. So you could make waves like this if you just agitated the end of a rope. But all of these waves, all of these mechanical waves, even though sound waves might look different than waves traveling on a string, they share similar properties, and we can understand how they all work by understanding the properties of just one of these kinds of waves. So if we remove all the damping from this wave, we get these perfect, pure, what are called sine waves because of their shape. And you see we've got a little frequency bar down here. So if you're curious about like what is frequency, well, so I can lower the frequency to exactly 1 hertz. 1 hertz would mean that in every second we have 1 wave cycle moving forward, right? Just as I talked about before. We can up that to, you know, what can we get here? I guess we can only go up to about 3 hertz. But there I'm at 3 hertz, so in this case we're producing 3 wave cycles per second. And as I mentioned, one of the other things that you'll be able to notice here is even though we're producing more waves per second here, the individual wave motion, like the movement of this crest, is not any faster, even though the frequency is higher. If I were to lower the frequency back down, and we were to look at this wave, even though this wave looks much slower, the movement of the energy through the medium actually is occurring at the exact same rate as it was in the higher frequency wave. So anyways, this is just kind of a cool simulation you can use to do that. You can add in rulers and a timer to do different things, kind of neat. So I'll wrap it up there, but yeah, the answer to the question, 440 waves per second.
That's a really cool interactive thing.
Yeah,
I'm
it's
gonna
useful.
use that when I
It really
teach.
is,
It helped my students a
trigonometry.
lot to understand it. It's kind of a nice way to learn in addition to all the examples we were seeing from the
Yeah.
sound wave.
No, absolutely. I think that's really great.